Okay. Alright, so hello, good day, ma'am. I'm Dan Melpol S. Saavedra, one of your student in Advanced Computer System Architecture. So in this video, I'll be discussing the cache mapping types, particularly the direct mapping, associative mapping, and set associative mapping. So before everything else, let's discuss what is a cache first. So a cache is a CPU hardware used by the central processing unit or the CPU of a computer to reduce the average cost or the time or the energy to access data from the main memory. So a cache is a smaller, faster memory located closer to a processor core which stores copies of the data from frequently used main memory locations. So most CPUs have a hierarchy of multiple cache levels like L1, L2, L3, and L4. So in here we have the fastest but the smallest in terms of size, and then we have a little bit larger, but slower in terms of speed. So we have the largest one, which is the L4, but in terms of speed, this is the slowest one. Okay, and according from an article of Geeks for Geeks, a cache is a small section of SRAM memory added between main memory and processor or the CPU to speed up the process of execution. So it is known as cache memory. So it includes a small amount of SRAM and more amount of DRAM. So it is a high speed and expensive memory. So that is all about in terms of the definition of a cache. So we have another thing that we guys need to take note in here. So we have here the cache hit ratio. So it is a measures how effectively cache fulfills the request for getting content. So cache hit ratio is being computed by this formula or equation. So it is equal to the number of cache hits divided by the number of cache hits plus the number of cache miss. So what is this cache miss or cache miss? So if data has been found in the cache, so it is a cache hit. Else, it is a cache miss. So I think it's very straightforward. So if it's on the cache, it hits or it is a cache hits. But if it's not on the cache, then it's a cache miss. So later on we'll discuss this one for this cache hits and then cache miss. Okay. So next thing is cache mapping. So it is a process or technique of bringing data of main memory blocks into the cache block is known as cache mapping. So we actually have three techniques that can be classified in terms of cache mapping. We have direct mapping. Second is associative, or sometimes it's being called the fully associative mapping. And then last is the set associative mapping. So each one of them have their own advantages, okay, and of course they also have their own disadvantages. So later on we'll discuss them one by one. Let us now talk about the simplest form of mapping. So direct mapping is a procedure used to assign each memory block in the main memory to a particular line in the cache. So we have here the advantage of direct mapping. So in terms of speed, this is actually the fastest. So search time is less here because there is one possible location in the cache organization for each block from main memory. But in terms of disadvantage, so each block of main memory maps to a fixed location, okay, in the cache. So therefore, if two different blocks map to the same location in cache and they are continually referenced, the two blocks will be continually swapped in and out, known as the trashing, or you could actually call that one as cache miss because there is now a conflict, but the most precise or the more precise term for that one is trashing. Okay. So how does this direct mapping cache work? So each main memory address maps to exactly one cache block. So for example, on the right is a 16-byte main memory and a 4-byte cache for a 1-byte blocks. So memory locations, say 0, 4, 8, and 12 all map to cache to black 0. And then addresses 15913 map to cache black 1. And then we have the 2, 6, 10, 14, which will go to black 2, and so on and so forth. So we actually have a better representation of that one. So 0, 4, 8, and then 12. So the white 1 will go to black 0. And then the 1, 5, 9, and then 13 will go to black 1. And then the 2, the green one, so 2, 6, 10, and then 14 will go to black 2, and so on and so forth. So this one is in the form of round robin. Okay, so it's like 1:1, but once the black 0 to black 3 is already full, then it will just loop back to black 0 and then black 3 again. So it will keep on going like that until all of our let's see lines right here is already transferred to our cache black right here. Okay, so we have here another example. So this one is in terms of actual example. So each block from main memory has only one possible. So this is just another definition of a direct mapping. So each block from a main memory has only one possible place in the cache organization in this technique. So for example, every block I of the main memory can be mapped to block J of the cache using the formula. So we have here the formulas. J is equal to I modulo M, where I is the main memory block number, and then J is the cache block number, and then M is the number of blocks in the cache. So the address here is divided into 3 fields. We have the tag, block, and then the word. So here is now the process. So to map the memory address to cache, the block field of the address is used to access the cache block. Then the tag bits in the address is compared with the tag of the block. For a match, a cache hit occurred as the required word is found in the cache. So if it's in that if there is a match, then it's called a cache hit. Otherwise, a cache miss occurs and the required word has to be brought in the cache from the main memory. So the word is now stored in the cache together with the new tag, wherein the old tag is being replaced. So in here, if you can fit that one, or if there is a match, then it's a cache hit. Otherwise, if it's not in there, then it's a cache miss. Okay, so this is actually the main problem. So later on we'll discuss more about this problem, but right now I'm telling you guys that the main problem of direct mapping is this cache miss. So it has this issue of let's see, conflict, okay, or that sometimes we call it one thrashing. Okay, so that is the main problem of direct mapping. So we have here the types of a cache misses. So we have number 1, the compulsory miss, or aka the cold miss, and then we also have the conflict miss, wherein it has two different types, or 2 types. We have the collision miss and then the interference miss. Okay, and then we have the capacity miss, and then so on and so forth. We actually have a total of 6 kinds of misses, but in here I will just talk about number 1 and number 2. Okay, or just actually number 2, and then just want you guys to know that this compulsory miss, conflict miss, and then capacity miss is the one that is being so-called as misses. So the remaining misses are not going to be discussed anymore, since this will only take the video or the presentation longer. So we have here the first one. The first iteration actually has a 40 misses, and then the second iteration has a 16 misses. Okay, so they fall under this number 1 or number 2. So we have a collision or interference, or even a cold miss. Okay, so this is the problem that is being encountered in a direct mapping. Okay, so we have a another example right here. So this is in terms of actual example, in terms of you know, if there is a certain computation or a number. So we have this one right here. So if we have a fully associative map cache of 8 kilobyte size with block size which is equal to 128 bytes, and say the size of the main memory is 64 kilobyte, assuming word size is 1 byte. So supposedly one word is 2 byte, right? But in this example, let's just assume that one word is equal to 1 byte to make things easier to understand. So then, number of bits for the physical address is equal to 16 bits. So in memory, in terms of memory size, that is equal to 64 kilobyte, which is equal to 2 raised to 6 times 2 raised to 10, which is equal to 2 raised to 16. So you can do the math later on. Just pause the video. Okay. So for the number of bits for word, it is equal to 7 bits. Okay. As block size, it's equal to 128 bytes, which is of course equal to 2 raised to 7. And then for the number of index bits, we have here, which is equal to 13 bits. As cache size, it is equal to 8 kilobyte per in. It is also equal to 2 raised to 3 times 2 raised to 10, which is actually equal to 2 raised to 13. And then for the number of block bits, so this is now where you're going to compute a little bit. So we have here a number of index bits. So we have this one right here, number of index, this one here, number of index bits minus your number of bits for words. So number of bits for words is 1. So we have here 13 minus 7, okay, which is equal to 6 bits. Or you can do this one, as another way up for computation. So we have the number of cache blocks is equal to cache size divided by the block size. So cache size is, where is that one? Let's find the cache size. It's right here. Okay, so cache size is actually 8 kilobyte, and then the block size is actually 128 bytes. So 8 divided by 128, 8 kilobyte rather, divided by 128 bytes is equal to 8 times 1024 divided by 128 bytes is equal to 64, or it is also equal to 2 raised to 6 blocks, or that one is actually equal to 6 bits also. Okay, so if you guys are going to take a look on this one is similar with the last computation right here, or the computation on the first solution. So number of block bits is equal to 6 bits, and the number of cache blocks is now equal to 6 bits. And then for the number of tag bits, so it is equal to the number of bits for the physical address minus the number of bits in index. So number of bits for the physical address is this one, which is equal to 16, and then number of bits in index is, where is that one? 13. This one, number of index in terms of bits. So it's 16 minus 13, which is equal to 3 bits. Okay, so I hope this one is clear to you. Anyway, that's it for the direct mapping. So let us proceed now to the next one, which is the associative mapping. So this is now the solution, okay, for the problem of a direct mapping. So this one solved the problem of direct mapping. So this one permits each main memory block to be loaded into any line of the cache. Like in direct mapping, it has that specific lines only that you need to follow. In here, as long as there is an available slot, you can put it anywhere. Okay. So here, the mapping of the main memory block can be done with any of the cache block. So the memory address has only 2 fields here. So before we have 3. So we have the tag, block, and word. So in here, we only have the word and tag. So we don't have a block in associative mapping. So this technique is called as fully associative cache mapping. So sometimes it's called associative mapping, or sometimes it's called fully associative cache mapping, or fully associative mapping. So either of those, they are just the same. So for this particular example, we're going to use the same given, okay, so that we can compare them later on. So we have a fully associative map cache, which of 8 kilobyte size, with block size is equal to 128 bytes, and say the size of main memory is 64 kilobyte. Then we have actually we have similar for the number of bits for the physical address. So we also have here 2 raised to 16, and then we have here a number of bits in block of offset. So that one was called number of bits per word in direct mapping, but in here we call that one number of bits in block offset. So they're actually the same. So it's 7 bits in here. It's also 7 bits in here. So as block size, it's equal to 128 bytes, which is equal to 2 raised to 7. So it is now differs in terms of number of tag bits. So in here, number of bits for the physical address minus the number of bits in block offset. So number of bits for the physical address is, where is that, 116, this one right here, and then number of bits in block offset is 1. So 16 minus 7 is equal to 9 bits, compared to the direct mapping. So the number of tag bits is 3. Okay, so we now have a different result in here, wherein we have 9 bits as a result. And then for the number of cache blocks, so we have the cache size divided by the block size. So cache size is 8 kilobyte, and then the block size is 128. So this one is actually the same with what we have in direct mapping. So we have a result of 6 bits in here. We also have here 6 bits as a result. Okay, but just have a different unit, so we call it 2 raised to 6 blocks instead of just a bit. Okay, so we have here a representation of a fully associative mapping or associative mapping. So in direct mapping, we have a specific line where we can put our data, but in here, okay, we can actually choose from this main memory. We can put that one in block 0, or in block 1, or even up to the last one. Okay, you can place it anywhere, literally. Okay, so the the data one right here can go to let's say this one right here, or this one right here, or this one right here. Okay, and so on and so forth. As long as that slot is free, then it will fit on that cache memory. So in here we have here a many to many relation. Okay, so here is now the problem of associative mapping, but before that I just would like to discuss this one a bit. So we have here PA bits, which is equal to your physical address bits, which is separated, or it has 2 sections. So the green one, which is the 6 bits, is the tag bits, and then the orange one is the black or the line offset. So as you guys can see, it is actually using a comparator. So one comparator for each conversion, or for one line of character. Okay, so that's how it's being processed from our main memory to your physical address, going to your cache memory. Okay, so we can actually use an XOR gate instead of an OR gate only, but that would be more expensive, so that is already a no-no. But if mine is not a problem, then of course I just use that one. But for the consumers, for the people who are going to use this kind of technology, so most of them, actually I'm one of them, so most of us are poor. Okay, so we wanted technology that is great, it's really okay, but low in terms of price. Okay, so OR gate is cheaper compared to XOR gate, but it's actually not that cheap. Still not that cheap. Still quite expensive. So in terms of performance and everything, and uh, in terms of rating, everything is very good in associative mapping. So the only problem is the price. Okay, so that is the main problem of associative mapping. So due to the need of comparators for every single character line, the cost of the implementation is too high. Okay, so again, in terms of functionality, in terms of uh, let's see, call this one on how this associative mapping work. It's already perfect. Okay, it's just the price. Okay, that is being compromised in here. So that is the main problem of this mapping. So let's just have a short recap. So in direct mapping, it's good because in terms of uh, speed, that is the fastest one. Okay, however, we have this problem, this conflict, this thrashing, this kinds or different kinds of misses. Okay, on the other hand, associative mapping is super good. It's actually too flexible in terms of functionalities. It's very good on its own. However, of course, it will be needing a lot of comparator wherein each comparator is already expensive. So having two, three, or four is already too expensive for that kind of mapping. So let me introduce to you the solution on both. Okay, for both. Okay, so we have here the set associative mapping. So this one solve the problem of associative mapping and then the direct mapping. So it has both the advantages of direct mapping and associative mapping. So the cache is divided into a number of sets of cache lines. So each main memory block can be mapped into any line in a particular set. The associative mapping just has a different or just a little bit tweak, okay, in terms of processing things, okay, or in computing things, okay. So we have this one right here. So instead of putting this zero anywhere into our cache memory, so we've actually uh, limited one into a set. Okay, so in this set 0, you can place this 0 right here to 0 in cache memory, or even in 1, or even in 2. Okay, so you can choose from any of this three. Okay, so same with number 1, so you can place it on in set 1. Number 3 is to the next set, and so on and so forth. So that is the solution, okay, in terms of solving the misses, thrashing, and then instead of using a lot of comparators. So this is a new architecture, a newer, let's see, formula, okay, or newer ways of uh, making this one cheaper, but in terms of performance, it's already great. Okay, so we have here one set is equal to k lines, wherein k way is the set associative. So later on we'll discuss what is this k way or k lines. Okay, so we have here a more clearer example of set associative mapping. So again, 0 can be placed right here. Let's say this 0 line right here in cache memory, or 1 line right here of cache memory. But in this example, it was placed on B0, okay, or in this 0 right here. Okay, for the number 1, it was placed on the third line, so it's now our B1. For the third one, okay, which is the B3, B2 rather, is placed on the fifth line, and then we'll just go back, okay, from the start. Okay, so 4 here will now go to your line 1, and so on and so forth. So your 5 here will now go to your line 2, so that's now B5 right here, and then 6 will go to your line 4, 7 will go to line 7 also in cache memory. Okay, so that's how it's being mapped in a set associative mapping. So in terms of actual example, so we have here the number of sets, so each of which consists of a number of blocks. So the relationships are n is equal to w times l, wherein w is number of sets, and then l is the number of lines in each set. Okay, and then n is the number of blocks in the cache. Okay, so we have here another formula, which is I is equal to j modulo w. Okay, so we have an example right here. So to map the memory address to cache using a set field in the memory address, we access the particular set of the cache. Then the tag bits in the address is compared with the tag of all L blocks within that set. So for a match, a cache hit occurs as the required word is found in the cache. Otherwise, a cache miss occurs and required word has to be brought in the cache from the main memory, and then according to the replacement policy used, a replacement is done if the cache is full. So again, we'll be using the same example, okay, like what we have in direct mapping and then the fully associative mapping. So if we have a fully associative map cache of 8 kilobyte size with the block size of 128 bytes, and say the size of main memory is 64 kilobyte, and we have two-way set associative mapping. So assume each word has 8 bit. So again, instead of 2 bytes or 16-bit, okay, for each word, we'll be using one word 1 byte, okay, or equal to your 8-bit. Then number of bits for the physical address is equal to 16 bits, as again in memory size it's equal to 64 kilobyte, which is equal to 2 raised to 6 times 2 raised to 10, wherein again we have the same result, which is equal to 2 raised to 16. And then for the number of cache blocks, we have the same formula, cache size divided by the block size. So 8 kilobyte divided by 128 bytes, so 8 times 1024 bytes divided by 128 bytes is equal to 2 raised to 6 cache blocks. And then we have here the number of main memory blocks, wherein it is equal to main memory size divided by the block size. So main memory size is equal to 64 kilobyte divided by your block size, which is equal to 128 bytes right here. Okay, so just do the math. So it's equal to 64 times 1024 bytes divided by 128 bytes is equal to 2 raised to 9 main memory blocks. Okay, and then the last one is the number of sets of size 2 is equal to number of cache blocks divided by the L is equal to 2 raised to 6. So number of cache blocks is 2 raised to 6 divided by L is a two-way. So according from here, it is a two-way, so L is equal to 2. So 2 raised to 6 divided by 2 is equal to 2 raised to 5 cache sets. So L is equal to 2 as it is two-way set associative mapping. So if it's three-way, then this is 3. If it's four-way, then this is 4. Okay, so as you guys may have noticed, we have the same result in the number of bits for the physical address. We have the same result for the number of cache blocks. We have the same result for the number of main memory. Let's say number of main memory blocks, and the, where is that one in associative mapping? Here in here it's just called number of tag bits, but they are same in terms of 9 bits. Okay, so they just differs in terms of the unit and then probably the name of that specific variable, but in terms of formula, they're actually getting the same variable. So in here, instead of just the size, okay, this map uh, size, it's now being called main memory. Okay, but still the same, divided by the block size, which is equal to 120. And then here is now, or here is just the new one, okay, which is the number of sets of size 2, which is the two-way, three-way, and so on and so forth. Okay, so just use this formula, and then you will get this one. So 2 raised to 5 cache sets. So we now have here the summary, okay, of each of the mapping. So for the direct mapping, so this one needs only one comparison because of using the direct formula to get the effective cache address. For the associative mapping, so this one needs comparison with all tag bits. For example, the cache control logic must examine every black tag for a match at the same time in order to determine that if black is in the cache or not. Okay, so again, they're using a comparator right here, which is an OR gate. For the set associative mapping, so this one needs comparison equal to the number of blocks per set, as the set can contain more than one blocks. Second, so mean memory address is divided into 3 fields. So we have the tag, black, and word. So the black and word together make an index. So the list significant tag bits identify a unique word within a block of mean memory. And then the black bits specify one of the blocks, and the tag bits are the most significant bits. For the associative mapping, we only have 2, so it's a tag and word. So instead of divided into 3 fields, this one is into 1 field only. And then for the set associative mapping, we have the main memory address is divided into 3 fields also. It is now the combination of this one and this one. Okay, or actually it's just similar with your direct mapping. Okay, we have the tag, but instead of black in here, it's called set. Okay, and then similar with word. Okay, and then for the third one, there is one possible location in the cache organization for each block from main memory because we have a fixed formula. Okay, while on the associative mapping, the mapping of the main memory block can be done with any of the cache blocks. So you can place it anywhere. Okay, while on the set associative mapping, the mapping of the main memory block can be done with a particular cache block of any direct map cache. Okay, so in here 1 is to 1. In here you can place it anywhere. In here it's can be placed into a particular cache block only. Okay, and then number 4, for the direct mapping, if the processor need to access same memory location from 2 different main memory pages frequently, cache hit ratio decreases. For the associative mapping, if the processor need to access same memory location from 2 different main memory pages frequently, cache hit ratio has no effect. Okay, again, in terms of functionality, this one is already perfect. It's just the price, okay, that we have to consider for this one. So for set associative mapping, in case of frequently accessing 2 different pages of the main memory, if are reduced, the cache hit ratio reduces. Okay, so in here the performance will also fall. Okay, so that is the thing that we guys need to take note. Okay, so it reduces the hit ratio if there is a frequent accessing 2 different pages. And for the last one, so search time is less here. In the direct mapping, search time is less here because there is one possible location in the cache organization for each block from the main memory. And then for the associative mapping, search time is more as the cache control logic examines every block's tag for a match. And then for the set associative mapping, search time increases with number of blocks per set. So the more blocks that we have in here, the more time that it will consume in searching that particular cache page or cache block. So here are my references for this report, and that is the end of my presentation.